Type 1 diabetes is usually diagnosed in people at a very young age. Only 5% of people with diabetes will end up having type 1 diabetes. In type 1, the pancreas produces little to no amounts of insulin, making it so glucose cannot be converted into energy that is needed by the body. Not only do people living with type 1 diabetes have to check their blood glucose levels constantly, but they have to inject themselves with insulin, where the common injection site is the abdomen. Humulin is a recombinant form of insulin that can be synthesized using E. coli, which takes in 2 strands of human insulin DNA, and this process can occur in a bioreactor. First, we will have 100 liters per hour of glucose and ammonia and 100 milliliters per minute of oxygen, which will go into the bioreactor. This will generate 1,000 liters per hour of biomass product, which will ultimately include humulin. Now, we'll show you how this process will occur.
So this is our unbalanced chemical equation, and we're going to make A, B, C, D, E, G, H to be the coefficients. And now we're going to write out the element balances for each element. So for carbon, it'll be and hydrogen would be 12A plus 3C is equal to 2.8D plus 1.9E plus 2H. And for oxygen, it'll be 6A plus 2B is equal to 1.8D plus 0.3E plus 2G plus H. And for nitrogen, it will be C is equal to 2.8D plus 0.3E. And then we have two information, which is D over E is 1 over 5, and G over D is 1 over 2. So given these equations, we can just plug in these equations into a matrix, and we get A is equal to 2.04, B is 0.88, C is 2.5, D is 1, E is 5, G is 0.44, and H is 9.84. So we can just substitute these numbers into the equation, and then we get the balanced equation.
Part B asks that we determine the inlet molar flow rates of glucose, oxygen, and ammonia in moles per hour. So we can use the known concentrations of glucose and ammonia to solve for their molar flow rates. So we multiply their concentration times the volumetric flow rate to get 15 moles per hour for glucose and 5 moles per hour for ammonia. Then we also use the given temperature and pressure to solve for the molar flow rate of oxygen. So we use the PV equals nRT equation and get that the molar flow rate of oxygen is 0.0289 moles per hour. For part B, we're asked to determine the limiting reactant, the reaction rate, and the fractional conversion of glucose. To determine the limiting reactant, we take the minimum value of molar flow rate over the coefficient, and using the 3 values that are going in, we get that O2 is the limiting reactant. Next, since there's only one reaction, R is equal for all compounds in the reaction. We know that the respiratory quotient is 0.5, which means that the molar flow rate of carbon dioxide over the molar flow rate of oxygen is equal to 0.5. Then we've solved that the molar flow rate of oxygen is 0.0145 moles per hour. And since no CO2 is entering the system, we can cancel out the molar flow rate of CO2 in, and then we can solve for R, which is equal to 0.033 moles per hour. Last but not least, we can solve for the amount of glucose leaving the system since we solve for R. We know the amount of glucose going in, and then we also know the coefficient as well as the R. And we can solve for the moles of glucose going out, which is 14.9 moles per hour. Lastly, we solve for the fractional conversion, which is equal to the molar flow rate in minus the molar flow rate out over the molar flow rate in, and we get 0.0047.